Hello, I'm Ardalan Nasri. I'm PhD student at EOS Laboratory Institut Électronique et des Systèmes, and I'm working on a model for the PV farms. Today I want to talk about a major challenge concerning solar energy, which may affect us all. As our planet gets warmer, we need to understand how climate change will affect our solar power plants, which is so crucial for our power transition. PV farms are developing very fast. Its growth is about 20% per year around the world. But there is a paradox. The climate change that we are trying to combat by using solar energy is actually reducing our production every year. It's actually like a computer or a laptop. When it overheats, the performance decreases simply. Some studies show that in 7 years, some regions could lose up to 50 kilowatt hours per year for each kilowatt installed solar panels. And it's due to rising temperature and not considering other factors that will change, like humidity or atmospheric pollution. This is a problem because the actual commercial power plants are working with narrow profit margins. So even a small reduction in power production can make them financially unacceptable. So this is where my research comes in. I am developing a digital twin. It's actually a sophisticated model of a PV plant, but there is something that makes it different with the other models. Instead of treating the system as one large system, I break it down into individual modules. It is actually like building blocks. Each module represents a component in the PV farm. For example, a module for the solar panels, another for the cables, another for the other electronic components. In each module, we have detailed physical equations that describe how it works in different conditions. Let's take an example. The solar panel module calculates the effect of the temperature on the efficiency, or how the radiation of the sun will convert to electricity, or even how some other factors like humidity or air pollution can block this conversion. The other example is the cable module, which calculates how the resistance in the cable will varies with different temperature, and it will affect the energy transmission in the network. When we connect all these modules together, we will have complete picture about the performance of our PV plant. The innovative part of my work is actually I combine the physical blocks with machine learning. It's like you give the physical equations to the computer and you let it to learn from the real data to be more accurate. I'm actually working with 2 companies and their real PV plants to validate my model, and I also feed my model with real measured data to improve its accuracy. The ultimate goal is practical. We want to help design solar systems that better withstand climate change. By understanding how each component reacts in changing conditions and non-standard conditions, we can identify the weaknesses and suggest some improvements and other technologies.